Okay. Hello, everybody. Thank you all for coming. I'm going to talk about performance, specifically performance of distributed systems. And I like to think about this as being the performance of the systems that are all connected and how they're connected. So it's the performance of collaborating services and of communication links. It's actually kind of simple when you start to think about it. But there's lots of interesting nuances. There are lots of mistakes we can make. And it's nice to have a framework for thinking about this. And really all we're thinking about is services and aggregations of services. And this talk is really just a framework for thinking about how these things perform, talking about how these things perform, monitoring how these things perform. So in my day job, I am doing machine learning to optimize systems automatically. So we do a lot of performance testing, benchmarking, machine learning of kind of tweaking configurations and trying to figure out how best to make a system perform. Before that, I was co-founder of SpringSource. So many, many years ago, I have now realized I did Spring Framework and wrote books about Spring. But I'm probably the least qualified Spring person in this room right now. It's very interesting. Writing some Spring Boot apps at the moment, no idea what I'm doing. I'm on Twitter, I'm on GitHub, I have a blog, and there's a lot of algorithms and equations in this presentation. There's a lot of deeper explanation on my blog. Please feel free to read and comment and criticize to your heart's content. So the agenda is quite simple. I'm going to talk about measuring, because if you don't measure properly, then everything else is kind of pointless. We're going to talk a little bit about how to find performance problems. This is only 50 minutes, so it's actually quite hard to do this talk in 50 minutes. Thankfully, Dave is doing a talk about Zipkin later, so he's removed the need for me to talk about that in great detail. I'm going to talk about finding candidates for optimization. So you've got these microservices, you want to figure out where to optimize. We'll talk a little bit about that. I'm very interested in modeling. Performance benchmarking and optimization is kind of expensive. You need to set up all these servers, all these databases, all these kind of different competing services to try and get something that's like production. So I'm interested in how you can model that, and there are any tools we can use to kind of refine our thinking. And I'm very interested in forecasting, in particular because traffic changes so quickly, code changes so quickly, we're scaling out, we're scaling up. We're interested in how to forecast. I'm not going to talk about tuning the garbage collector or tweaking what kind of page size you should use on Linux or anything like that. If you're interested in those topics, please read Brendan's book, Systems Performance. It's like the Bible on this topic. So one of the first things I found when I started working at Skipjack is that everybody means something different by performance. It's really interesting. So what do I mean when I say performance? I'm really talking about two things. How fast can I do a thing? And how many of those things can I do every period? Which should kind of sit with what most people think about performance. So really I'm just talking about latency, how fast, and throughput, how many. And many, many people will talk about throughput, or many, many people will talk about latency, but they don't often talk about the two in tandem. And actually, to get any sensible measurements or have any sensible discussion, we need to talk about them both at the same time. So throughput's really, really simple. It's just your rate of processing. It's X per Y. Requests per second, records per minute, messages per second, tasks per day, those kind of things. And we kind of all talk about this very instinctively when we're thinking about our systems. And it's the kind of standard specs, right? My database can do 10,000 queries per second or transactions per second or whatever. Those are the kind of things you see. Latency is a bit more complicated. It's the time taken for something. And it's the something where all the problems start to kind of creep in. You realize that everybody means something different by that something. Is it service time? Is it time to the first byte received by the client? Is it time until the first response is completed, or the last byte, or the time until the browser has rendered the page? All these things could be valid in certain scenarios. So the real first tip from this presentation is make sure you define what you mean by latency, so that when everyone in your organization is saying the latency is this, you're actually measuring the same thing. So as I've said, measuring is hard. And it tends to be where everything goes wrong, because if you have this kind of garbage process where you're generating these metrics and these measurements that actually don't mean anything, everything else you do downstream from that is basically useless. You can't derive any value from that. So getting the measurement right is very, very important. Put together this very simple crib sheet. There's not a lot really you need to know. Just don't get caught up too much in people telling you exactly what you should do. These are just hints. But the key thing here is when you're recording performance of a system, it really helps to record time-stamped requests with the observed latency and success and error. So effectively, you're storing data in the highest fidelity you can. It's every single request response, how long that request response took, and whether it was successful or not. And then from that, you can kind of calculate a whole slew of useful metrics. You can count for throughput, kind of min, max, mean, kind of useful. My maximum throughput is 10,000 requests per second, minute, whatever. And you can do that over various time windows, and it's very useful to do it over various time windows as well. You want to try and get like an hourly trend, kind of coarse-grained view of your system. But also very useful to know, how's it performing in like 10-second windows or second windows to see if there are any kind of weird spikes. Latency is a bit harder. If anyone ever says to you they're measuring average latencies, you should laugh at them and point. The average latency is basically useless. Here I've said mean just means meaningless. So if you're taking the arithmetic mean of latency, you basically know nothing about your distribution, because latency distributions are really weird. They typically have very long tails, and they have lots of peaks and troughs. So the mean could be essentially anywhere and tells you nothing. You're better off measuring percentiles, and the percentiles you have to you have to measure will depend very much on your business, and we'll see why that is. But typically, you're going to take 95th, 99th, 99.9th, and maybe some more fine-grained than that. But if you could only measure one thing, you can only measure one latency, percentile, you should measure the maximum, because the maximum is the worst you could possibly have. And if you can kind of get your maximum quite low, then you're kind of bounding the possible bad experience your customers can have. So latency is weird, and I said that already, but the ways people think about latency is even weirder. Latency is not exponentially distributed. It doesn't look like this very nice curve where we have some that are really quick, and then some that are a bit slower, and then some that are a bit slower, and it's this nice smooth graph. It doesn't look anything like that. And it certainly isn't normally distributed. We haven't got this kind of bell curve of latencies. If you ever see a latency graph that looks like that, somebody's basically just made that data up. It just doesn't look like that. You have all these weird outliers. You have heavy tails. It's multimodal, so you do have peaks and troughs. And the key thing to realize is that your users, will see tail latencies far more frequently than you think they will. And this is where people get confused by percentiles. They don't mean necessarily what you think they mean. I'm going to show you some examples of that. The key thing to understand is, what does latency mean for your business? Are you most interested in measuring service time? So how long does my code take to run? I recommend not measuring service time as your primary measurement. What you're most likely interested in, what's the observable latency that the customer sees? Which might be, how long does it take to render my website if you're kind of an e-commerce system, or if you're an API and you've got a lot of API consumers, it's likely going to be time to last byte, so the customer can do something useful with it. Measuring service time is this lovely illusion that everything's lovely and fast, ignoring the fact that you have a network, and those networks are unreliable, and they have varying latency, and all these things that are actually still part of your system's performance. So this is a graph of latency that we took from Pet Clinic. So we often use Pet Clinic for load testing our own benchmarking systems. The important thing to realize here is that this is a log scale, so this isn't linear. We've got 1 here and 1,600 here, but we've got 10 here. So many fall in this bucket here. There's loads, obviously. But then we have a little peak again, around about 10. Then we've got this heavy tail. And you can't see it here because there's only so many pixels, but there are some all the way out at kind of 1,600 milliseconds. And The one thing I want to point out here, actually, is this graph, when I first plotted it, was wrong. And there was basically a big gap here around about 0. And I wondered what that was. And I looked at the raw data, and we had loads of measurements where the latency was 0. Now, unless somehow Pet Clinic has found a way to defy the laws of physics, I'm convinced we didn't have 0 latency. Diving into it in a bit more detail, actually, JMeter was just truncating the latency, so it was rounding down, like something that was 20 microseconds or whatever, down to 0 milliseconds. So it's really important that you do these sanity checks on your data, and obviously, the higher precision, the better. Don't end up with, I think I had 1.5 million records of 0 milliseconds. Incredibly fast system. So this is what latency looks like, and it's useful to plot this. But it's more useful to think about what does it mean in the real world, like what do our customers really see? And this is where tail latencies become really quite important. So most people will think the 95th percentile means that 5% of my requests are worse than that. And they'll be absolutely right. And those people that might think, well, then 5% of my customers see worse than that, and the other 95% see better than that. And they will be wrong, because that's not how probability works. In actual fact, the chance of a customer seeing something worse than the 95th percentile or the 99th percentile or whatever percentile is a function of how many requests they make. And in a blog post, Gil Tenner from Azul Systems pointed to some research that said that the average number of requests made for a web page is 42, which is very incredibly awesome that it's 42. So this means that just to get a rendered web page, you're not making one request for the web page, you're making requests for the images and the tracking things and all the important things that Google wants to do to know where you're going. So you get this function. You actually get to figure out that the chance of a customer seeing something worse than the 95th percentile is about 88%. So basically everybody is seeing something worse than the 95th percentile every single time if you make 42 requests. And obviously, as this number of requests goes up, it gets worse and worse. So most customers will see tail latencies, and we can actually see what the impact of this is if we do a quick simulation. So I hope you can see all that. I'm very interested in this little simulation. Customers see latency worse than 95th percentile with probability 5% when they make one request. But if we say, OK, let's make like 10 requests, then now it's up to 40%. So there's an almost even chance there. And obviously, as the number of requests increases, we saw 42. It gets to 88. And it doesn't take long until it gets to getting close to 100%. And this is why, if you have a service where you're making a lot of interactions with the customer, you maybe have a chatty API, or you're doing websites with lots of images and lots of tracking things, it pays to track tail latencies way out past 95th. So certainly 99th, but also it pays to track maximum, and maybe even like 99.99, 99.999. And when we're measuring for our customers, we track those latencies because they're important. So it's just useful to realize people see latencies, worse latencies, way more than you think. This has just stopped working now, which is, oh no, it's back. The other interesting question, and I kind of alluded to this already, is whether or not we can talk about latency and throughput in isolation. This is the thing I commonly see when I talk to customers, especially the customers who will boldly state their system is designed for performance. I'm not quite sure what that means. They'll say, we can do 5,000 requests per second. That's great. How long does each request take? It could take 10 seconds to deliver each request, and you could be doing 5,000 requests per second. It's not useful to your customers, to your users, to talk about just that metric. It's kind of a vanity metric. And it always makes me think of this cartoon. And in the first panel, it's alluding to the bit in Star Wars when Han Solo says that he did the Kessel Run in 12 parsecs. And he's doing this in the first panel. And then in the second panel, this little droid comes in and says, Sir, a parsec is a unit of distance, not of speed. And Han Solo turns around and says, I told you not to boast while I'm bragging, not to interrupt me while I'm bragging. This is the kind of thing I think about when everyone says, this is my throughput figure, and ignores the important latency or important kind of capacity or load. So these are intrinsically linked. Does anyone know Little's law? Not very many. OK, cool. So Little's law is this amazing result from queuing theory, like way back in the 60s. And it tells us this. It tells us that the mean occupancy of a system is equal to the mean latency times the mean throughput. And while mean latency isn't a great measure, it's a great way of reasoning about relationships between things. And we can follow this through with some complex mathematics, which I was going to show, but then I realized I only had 50 minutes, and it was going to take about 50 minutes just to do that bit. But we get to this curve, which tells us that as the utilization of a system kind of increases, and we can think of utilization roughly as the relationship between how much traffic is coming in and how much we can serve. You know, your system's got a finite bound on how much traffic it can serve, but there's no real bound, essentially, on how much can arrive. So it's this ratio of offered load to actual throughput. And when we get to here, about 75, 80%, things start to get bad really, really quickly. And latency starts to get really, 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 really high. And basically, each customer is paying the cost of waiting for everybody else to wait and to complete. There's this huge overhead just in the queuing and in the waiting for other people to finish. So it's really important to think about this and think about how your throughput and how your reaction to offered load can actually affect latency. And the key realization is high utilization is an early warning sign of bad latencies. If you're setting up monitoring for your system and you're thinking about, where do I put my what often seem like completely arbitrary alerts. Often we see customers with alerts on 50% CPU usage or disk space is running out or whatever, and these seem arbitrary. But in this case, you can set some good measurements. We know that 80% utilization, so maybe 80% CPU over 5 minutes or 10 minutes, is a sign, maybe, that latency is going to really start to degrade quite badly. And you probably want to set it just a bit before that, maybe 65, 70%. And you can use these models and these algorithms to figure out how your system's performing. So high utilization, you need to stay clear. And from a microservice perspective, the most interesting thing, and it's obvious when you say it, but so many people don't think it, latencies stack. So if you've got a service that depends on a service that depends on a service that depends on a database, the end latency is kind of the sum of all those latencies, right? You've got to do all those things. You've got to make all those communications. And had this kind of interesting backwards and forth on Twitter with Josh about monolith versus microservices. And I get the microservice thing. I think it's interesting. But it's this naive move to just, let's make everything a microservice, because we seem to have forgotten that distributed computing actually has downsides. And it's like a lesson we've been learning for every 6 or 7 years. We learned it back with Corba, and we seem to be learning it with SOA, and now we're learning it again with microservices. Networks have latency, they have finite bandwidth, they're unreliable. All these things play in. So latency stack. Calculating how latency stack is quite hard. There are some analytical models based on queuing theory. You can basically just do some quick summations. There's some really cool simulation tools. So PDQ from Neil Gunther is a really good tool if you know R or Perl. But actually, Guesstimate is a really good tool. I'm going to show you 2 approaches now. I can't tell you how excited I am about Guesstimate. It's quite sad, really. It's just this little cool tool. So the simplest way of thinking about how latencies stack is just to think about them adding up. So I've got 4 services, the UI, the logbook service, the leaderboard service, and I've got Cassandra, which is my database, because obviously that's still part of the distributed system. And we can start to tick these latencies up and see how they affect each other. So, well, Cassandra's going to be doing some stuff, so I'm going to put that around about 50%. The leaderboard is doing a lot of very interesting calculations, so I'm going to put that up there. The logboard's hardly doing anything. And then the UI, well, it's JavaScript, so probably way up here. That was a cheap shot. And you can see like it's really simple, just addition, and we've got this kind of total latency at the end. But as one of these systems starts to get overloaded, things start to get really bad. And one thing's interesting is the UI, the logbook, and the leaderboard, they're kind of the services that are the application. Cassandra may well be a shared database. Other services might be using it. It might be a shared server. So it's interesting to think about what happens when Cassandra like starts to get overloaded. So if we increase Cassandra's utilization, then the total starts to go up. But actually, when we push it over 80%, all of a sudden it's kind of gone higher. And then it's kind of going off the charts almost as we start to push that latency out. So it's interesting for microservices to think about not just how your little view of the service world operates, but what happens if there are other services sharing my infrastructure? And that could be something as coarse-grained as a database, but it might be something like a load balancer or some disks or a SAN or some network. These things all interact. And I think there's still some interesting research to be done to figure out how that all plays in together. So now I'm going to try to see if the demo gods will let me do this. Oh, that's looking all right. I've got to sign back in. So this is a great tool by Ozzy Gunn, I think his name is. It's called Guesstimate. And it's kind of like spreadsheets for probability. It's incredible, actually. So here I've tried to wire together, I think I can hide this bit, try to wire together what my system looks like. So I've got Cassandra over here, and I've got logbook and whatnot. And I've tried to simulate what the latencies are. So these are latency distributions. So this is, I've used exponential distributions just for this demo, but you can actually paste real data in here, and he'll generate that. And what's happening here is these are all tiny little Monte Carlo simulations. He's basically, here's a distribution. I'm going to use Monte Carlo to sample from that. And therefore, even if you can't kind of describe your distribution analytically, which you necessarily can't for some of these empirical distributions, you can still sample from it, and you can still run these simulations. And we can see how it's kind of all stacked up. And if we look at how logbook is constructed, it's got its own exponential distribution with rate 1 over 30. It has whatever YA is, which I think is the Cassandra, and YX, which is the leaderboard. But I've added some overhead here, a little latency overhead, which is the network communication. And I'm kind of simulating like a synchronous communication here. And we can try to think about what happens if we tweak that in one direction or the other. So if I make this 1 over 700, sorry, it's like this really slow synchronous connection now, or that synchronous bandwidth starts to get hammered, you can see how all of a sudden the UI starts to get this really bad latency. If I make it a lot smaller, then you can see that actually now there's not much overhead here in the leaderboard from the raw leaderboard core, and the UI times go much slower. And I like to use this to think about what's the impact of making some link between my services asynchronous rather than synchronous. Obviously, the overhead of an asynchronous call is a lot lower than a synchronous call, especially if you don't have to wait for that response, or you can defer the wait for that response. You can kind of just fire and forget. So it's a nice way of just thinking about how to kind of model these systems. And because you can fire in your real monitoring data, your real latency distributions, you can just simulate this to your heart's content. It's just a great tool. I'm really kind of impressed by it, as you might tell. And one of the interesting things that we can look for with these simulations is something that Nygaard talks about in the Release It book, which is this notion of an SLA inversion. It's this idea that we have some services arranged in a graph, and kind of the outer services have some SLA that's probably visible to our customers. Maybe we're saying we want to give a kind of like 1,000 requests per second throughput, 95th percentile latencies of 50 milliseconds. And for that to happen, you've got to think about how that flows back through that graph of services. And all those services downstream have to have a better SLA than that. And he talks a lot about what happens when one of those services just goes wrong, or there's some kind of degenerate scenario where all of a sudden it starts performing incredibly badly, and it kind of falls backwards towards the user. And we can model the impact of this with these simulations. And if you haven't read this book already, I urge you to, or the more modern kind of version of this is the Google Site Reliability Engineering book, which I'm slowly working my way through. It's pretty good. But it talks about all these topics. It talks about, we've got this complex cluster of machines, and the services are all wired together in these ways, and we've got these, what they call service level objectives, these kind of latency and throughput goals. How do we make sure that happens, and how do we monitor for that? It's very interesting. And it's from Google that the DAPA, is DAPA the work came from, which is this kind of notion of distributed tracing of microservices that led to Zipkin that Dave's going to talk about later. So very few of you knew Little's law. Who knows Amdahls law? OK. Not as many as I was thinking. So Amdahls law we can think of as a bit like Moore's law. Who knows Moore's law? OK. So Amdahls law kind of sits alongside Moore's law, and it tells us in the most common usage about how we parallelize our workloads. It tells us kind of, what's the improvement we can get if we're parallelizing something. But we can also apply it to microservices. It can tell us a lot about where we should focus our optimizations in a microservice architecture. And I'm always interested in this question, because people pay me money to do this. How much improvement can we get from an optimization? And there's this complex equation here, not so complex equation, but it's got this really instinctive intuition. And the idea is that the theoretical improvement in latency, given a fixed workload, is kind of proportionate to the amount of time you spend elsewhere. And if you work this through, you can figure out that the limit of speed up is basically proportionate to the amount of time you spend in the bit under optimization. So thinking that through, the theoretical max is limited by the parts of the system not under improvement, which just makes total common sense, right? If you spend only 10% of the time in the bit that you're optimizing, then you're not even touching the bulk of the execution graph. You're spending 90% of the time elsewhere. And we can figure this out by using Amdahls law. And if I look at our little service again, so we've got the UI, we've got the logbook, the leaderboard, we've got Cassandra. And roughly this is how much time we're spending in each of these places. And we can kind of figure this out using distributed tracing. We can get some idea about where's the rough distribution of time spent across each core graph. Then if we apply Amdahls law, we get, what's the rough improvement factor? Well, if I was to spend some time optimizing the logbook, I've got a theoretical max of only 1.1 speed up factor. But if I spend some time working on Cassandra, I can get like 1.67. So very simple calculations on our actual observed metrics in our system, like how long are we spending in each service, can tell you where to spend time optimizing. Optimizing is an expensive thing. It takes programmer time. It takes test infrastructure. It takes machines. You definitely don't want to waste time optimizing something that you're not going to get any value out of. So you want to drive your optimization choices by where the services are getting hammered. Where are you spending the most of your time? So this is an interesting thing, and people are interested in Amdahls law, but I'm much more interested in a kind of law that subsumes that, the universal scalability law. Who's familiar with the universal scalability law? OK, this is great. Hardly anybody raised their hand. I think nobody. So we're all going to learn something new. And this, I think, is from 1997, Neil Gunther. And it gives a surprisingly accurate model of how systems perform under load. And it tells us a lot about the future performance, where the high points are, where the low points are, and helps us really think about how our system's performing. And it turns out it applies to way more than just systems. It applies to organizations, like how your organization performs and how much work you can do within your business. It applies to agile processes. It applies to many, many things. But it answers a really interesting question. Can increasing capacity reduce performance? Like, if I add more servers, will my performance go down? And obviously, if you listen to the vendors, everything is linearly scalable. Now, I don't know if you know that. By that, they mean non-linear, but it's that linear with some factor that they kind of factor in. It's weird. But effectively, every system does not scale like a line, right? You add more servers, there's more points of contention. And it's trying to figure out where things go wrong. When should I expect to see things get worse? So the answer is yes. Things will get worse as you add more load, or as you add more users, or as you add more servers. And you can predict this. You can monitor this. The universal scalability law is this. It says that the relative capacity with n And n could either be the number of users or the number of machines, depending on which angle you're looking at the problem from. Is basically proportionate to this. It's the number of users or machines, and then you've got this kind of denominator here that's actually kind of interesting, but it's easy to break it down. The one factor here is what it would be if it was linearly scalable. The alpha factor here is the overhead of contention, so waiting for some shared resource, like the network bus, or just queuing, basically, just sitting, waiting to be served. And obviously, it's proportionate to the number of users or machines. And then we've got the beta factor, the crosstalk overhead. This is the most interesting one. This is quadratic in n, so obviously it gets worse really, really quickly. And this is the overhead of crosstalk, of components having to all agree on something. And this could be something as broad as your Cassandra cluster having to reach quorum on some value all the time, or as narrow as your processor having to liaise with NUMA nodes on the different parts of the machine to figure out where the memory is and kind of handle the cache coherence. But at some point, every system, unless it's incredibly amazing, will have this beta factor, and it will have this kind of retrograde performance. So this is what I think about when I think about it in my system, in my logbook system, is I've got Cassandra, and there are some bits of the data that I'm kind of interested in. I'm not as happy to accept maybe some eventual consistency guarantees. I want to get a quorum. And when I ask for a quorum, this whole consistency protocol kicks in, and everyone has to agree. And that's my limiting factor. That's my beta factor. And we can visualize this, which is the most interesting thing to do, I think, because it's hard to get the intuition until you see how the factors affect each piece. That's not the one. OK, so hope you can all see that. Here we've got alpha is 0 and beta is 0, so no contention, no crosstalk. So this is a system that's linearly scalable. As n goes up, Cn goes up. And this is basically what we get if we don't have any of those alpha factors or beta factors. Now, it pays to then think about what happens if there's some contention. Maybe I'm queuing as I arrive at my web server. Oh, I'm not even going to go that far. So a very tiny alpha factor, and we've diverged incredibly far from linearly. And actually what happens is this kind of approaches an asymptotic max, and we'll just kind of sit there. And if you were paying attention, I know it was kind of quick, but if you go back and think about this, and you work these algorithms through, if the beta factor is 0, then the USL, the Universal Scalability Law, is equivalent to Amdahls law. It basically puts the max on how we can perform. It's incredibly useful to kind of track these things. I'm going to talk about how you can track them in a minute. If we just back off on that a little bit, because it's kind of terrible performance, and we add a small amount of crosstalk in, you can see, like really quickly, it gets really bad. So this is the bit we need to be worrying about. We kind of reach this maximum, but then actually performance starts to degrade incredibly quickly, and eventually it will reach 0. That's kind of the intention, right, is that you can just load your system so much that it can't even move. The overhead of just trying to move means you can't move. And this is all well and good in theory. How well does it work in practice? Well, actually, it works incredibly well, and you can measure these things empirically for your system. And that's what I want to show you now. So I suspect I'm probably the only person who is going to use R in this conference. But I've got some data. And these are measurements that, of a benchmark on a Citrix, on a Cisco router. And this is the number of users, and this is the kind of throughput that was measured. And I've got the real data, like the full data for 1 to 32. But in production, you're probably not going to get that, or even in benchmarking, you're not going to get that. So I'm interested in wondering, like, what can we find out from this? Can we figure out like how our system's going to perform? And the answer is yes. So first thing I've done, and I'm going to be very quick with the R stuff. You don't really need to understand it in too great a detail. I've loaded some data into my R, and you can see these kind of data frames here. Then I'm going to plot what those points look like. So this is that kind of disparate data we've got. And it's looks incredibly different on here. It's plotting the number of users against like what the throughput was. And we can see there's like a little curve here. But from that data, we might expect this is never going to go downhill. We might expect that's going to reach some max. It's going to stay there. What I'm interested in doing now is trying to figure out how do we figure out what the alpha factor is, what the beta factor is, and then play that in and do some modeling. And if you're using R, this is incredibly simple. If you're using Java, it's not so simple, I don't think. But basically, we're going to do regression analysis along these points. This is not a line, so we're going to do nonlinear regression, and we're going to try and fit a curve based on the USL algorithm to that. And in R, that's really simple. It looks like this. So I've described the USL here as a kind of R function. And this NLS is nonlinear least squares regression analysis. The precise details are kind of irrelevant. And also, like, the thing about R that I found is you don't really need to understand it that much. You can literally just kind of reproduce this from reading a book and apply this analysis in your own business. It's kind of simple. But what we're going to get from this is an alpha, beta, and a lambda. The lambda factor is kind of irrelevant, but it just kind of gives you a magnitude of what the throughput is at each tick. And from this fit, we're going to find out what alpha and beta are. I don't know if you can see this here. So the alpha factor is like 0.0116. The beta is not. No. Those numbers are meaningless. Where they become very meaningful is when we start to plot them against projected load. So what would happen if we had 32 users or 64 users or whatever? We can plot that. And I'm also going to overlay the raw data for measurements up to 32 to see how accurate we were. Scroll this out a little bit. So the line here is the projected capacity, and you can see it's kind of got that retrograde performance here. Now it's going downhill. We know that at some point it's going to kind of reach 0. And it doesn't precisely match the actual measured data beyond the points we've got, but it tends to get the kind of trend right. And obviously, the more data you can gather, the better. And we can kind of think about that if we were to go back in and add another data point and see what would happen. So this is the raw CSV. And this goes up to 32. And this is my subset of that. So I'm going to take the point at like 27. I'm going to put that in here. I'm going to come back and run this whole thing again. And now you can see the fit is so much better. It's actually like got to here, it's kind of tracking these upper points, and it's roughly the same downtick as the measured data. Obviously, the more data you gather, the more accurate your prediction is going to be. But you don't need a lot of data. You need about 6 data points, kind of evenly spaced. So if you can maybe get like 1 user, 2 users, 4 users, 8 users, 16 users, whatever, some pattern to that, you can kind of do a decent match here. Then you can make a prediction, and you can make 2 predictions. You can say, right now we're dealing with 200 users on average per second. If we were to hit 300 users per second, we'd reach our maximum throughput. If we were to reach 350, we'd very quickly start to go downhill in terms of throughput, and actually everyone would start to suffer. You can also do that the other way around. You can say, right now we're running 4 servers, and our throughput is this. If we were to run 6 servers, we'd reach our maximum. If we were to run 8 servers, we'd start to have retrograde performance, and we can kind of use that to do capacity planning. It's actually relatively hard to do it per server, unless you've got a lot of servers, as you might imagine, because getting those 6 points separated out. So you can do it based on cores or on kind of hardware threads. Like if you've got maybe 4 servers, they've got 4 CPUs, each CPU's got 2 hyperthreads, then you've got a lot of data points. And you can start to turn those CPUs off or turn those servers off and figure out how that affects your system. And you don't even need R for this. So in his book, Guerrilla Capacity Planning, Neil Gunther, who kind of defined the universal scalability law, he, have I got the cover here? He has an Excel spreadsheet that you can basically paste your results into, and it will tell you when you're going to see this performance. So one of the things I like to get our customers to do, and we actually use this as part of our benchmarking methodology, because if you think about trying to figure out, without any prior knowledge, how well a system performs, you kind of have to push through warm-up periods. You have to figure out what the real maximum is. And you can use the USL to kind of predict where these maximums are, where these kind of downticks are, and you can kind of keep stressing the system. So we talk a lot about measuring crosstalk, and the way to do that is to try and measure throughput at different loads and then fit it to the universal scalability law. Two great things you should read. It's a very small ebook by Baron Schwartz, Practical Scalability Analysis with the universal scalability law. He takes it a step further and talks also about trying to figure out a very interesting thing, which is at what throughput does my latency start to go beyond my acceptable bounds. For many people here, that will be a very interesting thing to figure out, especially if you have consumer-facing systems where typically latencies do kind of correlate to conversions. You are going to want to try and do that analysis. The book that has all the details is Guerrilla Capacity Planning. I realized when I came to write this talk that I'd lost my copy, which really distressed me. So I bought another one. It's really expensive at the moment. It's like £50, 250 pages. But it's worth every penny. And I recommend, if you've never thought about capacity planning or any of those issues, it's kind of the only book you need. It's really, really useful. So I'm going to summarize for a few minutes, and I think we've got some time for questions. Of all these things, you're probably already doing some measurements. I think everybody measures performance in some way. You're going to get measurements from Spring Boot now, if you're using the actuator. But it's really important that you do something useful with them and that you track them properly. So Spring Boot does a good job of kind of tracking the raw data and then giving you these means to send it onto your systems. Is it InfluxDB or Elastic or whatever you might be using to track it? But the rule applies, garbage in, garbage out. Spend some time making sure that what you're measuring and how you're measuring it is accurate. You can monitor your utilization, and you can use that to derive decisions about when you think things might go wrong. Little's law applies here. Very simple rule of thumb, like incredibly simple. I find it useful to think about per user latency as well as per request latency. So what latencies were users seeing? And you can also correlate that quite nicely with kind of conversion. And if you're using Google Analytics as well, it's kind of nice to mess that data in there and try and figure out, in your business, does latency really have an impact on conversion? There's a lot of research that shows that it does, but maybe it doesn't for your business, or maybe it has a worse impact. You don't know. You can use Amdahls law to figure out where to optimize. And if you're having a problem with that, come and talk to me. That's what we do. We can help. But also, the most important thing for you to be monitoring is your scalability. It's useful to know how your system's performing now, and people are interested in that. But that's kind of largely a solved problem. There are some great tools out there, AppDynamics, New Relic, whatever. They tell you this is what's happening right now. Not so many tools to tell you what's going to happen in the future. And I think that's the most interesting thing. You want to know how your product's going to react to new users or new servers. I have a little reading list here. I think I've been through these already, but do read Michael's book, especially Brendan and Greg's book, Guerrilla Capacity Planning. Great books. And I think I've got 5 minutes left for questions. Dave.
So, about crosstalk.
Yes.
So you mentioned Cassandra and consensus as sort of an example of that. Have you got any more? And have you got any sort of models for thinking about that? And where does it come from? If I'm writing just a web server that's talking to a back-end service, I don't think I'm doing crosstalk. So where is it coming from?
You're almost certainly doing crosstalk in that case, depending on the architecture. If you've got NUMA, so you've got non-uniform memory, then each processor has some memory that's remote to it. Then actually the coherence protocol for moving memory about is typically your area of crosstalk there. And you do see it. Like, you do see it in those servers when you start to map that throughput. You'll see that higher load, you pay that factor. But also actually in Java, locking. So any kind of synchronization is really crosstalk, because every thread's trying to reach agreement about what the state of that lock is. And that tends to also then push down into the NUMA because you're doing that at the memory level. It doesn't just need multiple servers. There's plenty of crosstalk on a single server. Any more questions? I can't really see up there now. Wow, no. OK, well, thank you very much. If you have any questions, come and ask me afterwards, but I'll let you go and have your lunch.